So welcome back, and we're going to be talking about 2.2 today, are all atoms equal? We have a quote from Eleanor Roosevelt for today. Eleanor Roosevelt was quoted as saying, "Great minds discuss ideas, average minds discuss events, and small minds discuss people."
Please submit your attendance. Thank you.
So our learning goals for this portion of our unit will be to understand the process by which ions form, differentiate between atoms, ions, and isotopes, and then finally calculate the average atomic mass of an element. What you should already know from our previous lessons coming into this one is that atoms are made of protons, neutrons, and electrons. You should know that protons are positively charged, electrons are negatively charged, and neutrons do not have a charge. Protons and neutrons make up the total mass of an atom because electrons are too small to add up to a measurable mass. And that there is experimental evidence that has led to the development of our current atomic model. The model we're going to be using for the rest of this unit will be the Bohr model. The Bohr model shows neutrons and protons in the center with the nucleus and electrons in orbits around the nucleus. So here's a review from some of the previous classes, maybe possibly middle school courses. We get details about the subatomic particles. So first, your protons are what determines the identity of an element, of an atom. So it's always going to be the number of protons that tell you what element we're talking about. So if we're talking about carbon, if we know the number of protons for carbon, which is 6, any atom that has 6 protons is going to be a carbon atom. If you know that you are looking at an atom that has 7 protons, that would be a nitrogen atom. You can determine the number of protons by looking at a periodic table. In a periodic table, we have element symbols that are listed in the center of each square, and at the very top is a whole number, and that whole number is the number of protons. So every helium atom in existence has 2 protons. If it didn't have 2 protons, it wouldn't be helium. Number of protons is at the top. And the number of protons never changes because that would cause your element to turn into a different type of element. Now I have another way to show you the number of protons in a system called nuclear symbol notation, and I'll introduce it to you here. It just takes the proton number, and instead of it being on top, it places it at the bottom, and it takes the mass number and places it at the top. So as a review, your mass number is protons plus neutrons. It's listed at the bottom in your periodic table, but using nuclear symbol notation, we've moved it to the top. And we're going to be using nuclear symbol notation a little bit later on in the presentation to determine the number of subatomic particles called neutrons. So here's a developing level question. All we're doing here is we're looking at the atomic numbers, which is equal to the number of protons. And we're going to identify which of these elements have these particular numbers. So if we're looking for element number 27, if you go to a periodic table and you find element 27, and you can see in the top left corner of the screen, you see cobalt is listed with a 27 on the top. That tells you that there are 27 protons in a cobalt nucleus. So our first element is going to be cobalt for 27. And we'll take a look at this one at the bottom. We have 19 for our atomic number, so we have 19 protons. So we go to our periodic table. we open up where it says 19, we click 19, which is potassium. 19 is on the top, it's the number of protons. So you can see by just identifying the number of protons, you can identify an element. If you're curious, californium is 98 and iron is 26. Okay, to determine the number of electrons, we have to understand that all atoms that are in the periodic table are neutral. And that means they don't have any charge at all. No charge. Remember that our protons are positively charged and our electrons are negatively charged. So to determine a neutral atom, we have to have the same number of protons as we have electrons, because our positive charges in combination with our negative charges should equal 0. So when we're looking at our periodic table, if we see we have 2 protons and it's an atom from the periodic table, then we should know that we have 2 electrons in addition to that. And if looking at nuclear symbol notation, we can see we have 9 protons. And since this is a neutral substance, the fluorine, then there should be 9 electrons in addition. Okay, so this is really super simple. So these again this is our atomic number on this side, which is the number of protons. So if lithium has 3 protons, then it must have 3 electrons. Magnesium has 12 protons, it must have 12 electrons. And that is when we're talking about atoms on the periodic table, which are always neutral. All right, determining the number of neutrons. So I have moved the nuclear symbol notation up above the periodic table notation because I'm going to focus on that particular way of writing out your number of protons and your mass number. So neutrons are always determined by looking at the atomic mass, because your atomic mass is going to be the number of protons added to the number of neutrons. Remember that your protons have mass, your neutrons have mass, so if you add them up, you get the mass of your element. We don't add the electrons because they don't weigh enough to be significant. So you can see here what we've done in nuclear symbol notation. Our top number for fluorine is 19. That's our mass number. Mass number is going to be number of protons added to number of neutrons. And our atomic number at the bottom is only number of protons. So if we use this setup and we subtract our number of protons from our mass number, we're left with a value at the bottom, 10, and that's our number of neutrons. So we can say for fluorine, we have accounted for 9 protons. And since this is from the periodic table, we're going to say that it also has 9 electrons, and it has 10 neutrons. And I use a little 0 to show the charge of the neutron, just like I use a plus and a minus sign for the protons and the electrons. So these are the number of subatomic particles found in a fluorine atom. So let's calculate the number of neutrons found in some of these. Look at our first one. So our first value, aluminum, remember the top number, 27, is number of protons plus number of neutrons. And our bottom number, our atomic number, is only the number of protons. So if I take and I subtract the 13, hold on. If I subtract the 13 from the mass number, I get a value of 14 neutrons. So I have 14 neutrons in aluminum. I have 13 protons. And since this is an element that came from the periodic table, then I'm going to know that it has 13 electrons to make sure it's neutral. All right, we'll do one more. We're going to do one of these down here. So you can notice that we don't have a proton value listed at the bottom, but I wanted to make sure that you understand that this periodic table is always available to you. And if you can find sodium, you can see that number 11 on top is the number of protons. So you can plug that value in, 11. And if we subtract 11 from the mass value, you're going to get the number of neutrons. So it's going to be 12. 12 neutrons. And then for sodium, we also have 11 protons, which we just discovered by looking at the periodic table. And since it's a neutral atom, we also have 11 electrons. All right, this slide actually has some mistakes in it, so we're not going to go through this slide. It's just more of the same kind of practice. So remember that the number of neutrons does not determine the atom. It's not the number of neutrons that determines the atom. The number of protons is what determines the identity of the atom. Neutrons only contribute to the mass. So let's see if we can find the identity of some of these atoms. So if you have an atom that has 34 protons and 79 neutrons, you need to only pay attention to the number of protons, because it's the protons that it tells you whether it will be selenium, hydrogen, or helium. So we'll go to our periodic table again. And we had 34 protons. So where's 34? Here it is. So it looks like that's going to be selenium. And honestly, we don't care about the number of neutrons when we're just making the identity of the element, because the neutrons don't contribute to the identity. Neutrons are not important for identity. Let's take a look at this one down here. 2 protons. 2 protons would be this one here. So it looks like it's helium. And this last example, something that has 73 neutrons. Well, we can't tell what that element is because the neutrons have nothing to do with identity. So here are 2 scientists that worked to develop the idea of a kind of an atom called an isotope. The first one is Marie Curie, a French naturalized scientist, and some interesting facts about her is that she's the only woman to have won 2 Nobel Prizes, and her daughter also won a Nobel Prize. And in back before 1911, she was developing methods to separate different kinds of atoms, and those types of atoms were called isotopes. And then in 1913, a scientist by the name of Frederick Snoddy used her methods, and he found actual evidence of the isotope's existence. So what is an isotope? So an isotope is versions of the same element. They have the same number of protons, but they have different numbers of neutrons. Here are 2 examples. These are both isotopes of the element helium. These are both helium atoms. In one of the helium atoms, we have 1 neutron. In the other helium atom, we have 2 neutrons. Remember that what makes helium helium are the protons. So these blue spheres are your protons. Helium has 2 protons. But these 2 types of helium have different masses. This helium on top has a mass of 4. So we use hyphen notation to show that it has a mass of 4. And this helium in the bottom has a mass of 3. So we can use hyphen notation to show that it has a mass of 3. Hyphen notation is really useful when you're having to type answers into a computer instead of handwriting them, because with hyphen notation, we don't have to use subscripts and superscripts, which can slow down the process of recording information. So again, we have 2 kinds of helium. Helium-4 on top here, and helium-3 on the bottom. Now, we do use nuclear symbol notation, which I introduced to you earlier in the lecture. And nuclear symbol notation determines shows the number of protons and the mass number for each type of isotope. So I expressed in the last slide that helium always has 2 protons, so that's going to be the number at the bottom. and it's the protons that make it helium. So we have to always have 2 for helium. If it was 3 protons, it'd be lithium. If it was 1 proton, it'd be hydrogen. So we have 2 protons, and the number on top, this is going to be the number of neutrons plus protons. Number of neutrons plus protons. So this is your helium 4 in hyphen notation. Let's see if I can get my color changed. And the bottom one was your helium 3. Okay, so the procedures for writing out nuclear symbol notation are listed here on the right. The first thing you want to do is identify the actual element and write its symbol. And then you want to write the atomic number on the bottom left corner, and you want to write the mass number on the top left corner. Now, since we're doing everything digitally, and sometimes it's hard to handwrite things using Cami and programs like that, it's acceptable for you to write your mass number on the top left corner, and then you can move your atomic number to the bottom right corner if you need to, because it's hard to get a superscript and a subscript right over the top of each other. It's hard to put in some programs to put a subscript right under the 4. So I've seen it written this way, and that would be acceptable also. So a practice problem, let's write the nuclear symbol notation for carbon. So the first thing we want to do is identify the number of protons to determine the element. Well, we've already told you that it's carbon, so number 2, we're going to write the symbol for carbon. And carbon symbol is C. And then you can see the next step is to write the atomic number on the bottom left corner. So I'm going to go to my periodic table just to verify. And it looks like my atomic number is a 6. And then I'm going to write my mass number on the top. Now be careful, because they gave you specific information about the mass here. If you go to the periodic table and you just try to write the mass number that's on that resource, you're going to write 12.011. We need a whole number there. We don't want the decimal. And later in the lecture, you'll learn why we do have decimals there. So we want to use the information in the question. They tell you there's 8 neutrons. We already know that there are 6 protons. So to get the mass number, we're going to add them up, and it would be a total of 14. So this is carbon 14, and it's one of the isotopes of carbon. The most common isotope of carbon is carbon 12. We also have carbon 13 and carbon 14. There's 3 kinds of isotopes for carbon. Carbon 13 can last in nature for over 5,730 years. So this is often used to help identify fossils because it doesn't degrade quickly. Carbon-12 will degrade very, very fast, and most of you and most living organisms are made up of mostly carbon-12, but we all have a little bit of carbon-13 in us, and that allows scientists to be able to determine how old fossils are in some cases. All right, so we're going to go to a slightly different topic at this point. We're going to talk about those average atomic masses that are in the periodic table and why they have decimals. So if the number at the bottom of the carbon is supposed to be the number of protons and neutrons, then if we're just adding protons and neutrons, it seems like you should always have a whole number there. But we always have decimals, which means that there's a little bit more of a complicated system in calculating the number of the atomic mass number for your elements. To calculate the atomic mass number for the elements, we have to keep in mind that there are different types of each element. Here's the 3 examples. We have 3 kinds of hydrogens. There's hydrogen 1, hydrogen 2, and hydrogen 3. And 98% of all the hydrogen in the world is hydrogen 1. This is what we have the most of in our lives. And hydrogen 2 actually has a proton, but it has a neutron that's been added to it, and hydrogen 3 has 2 neutrons. Okay, so 99.98% of all hydrogen is hydrogen with a mass that is this mass right here. Then we have a very, very small percentage, and an even smaller percentage that has the following masses here. So what we need to do in order to calculate the number that's on the periodic table. We're going to try to calculate this value, 1.008. What we're going to do is we're going to use what's called a weighted average. A weighted average. So weighted average is basically how your grades are calculated also. So your daily assignments are 40% of your grade, and your test scores are 60%. So you guys can hear that bell ringing. I'm going to need to call it quits here, and I'll continue in the second part of this video with the rest of this problem.